Have you ever really thought about the food in your pantry? I mean, really thought about it? Today, we're going to pull back the curtain on this invisible ingredient, this hidden scientific rule that dictates why some foods last for days and others, well, they seem to last forever.
Okay, let's just dive right into the weirdness. Here's a puzzle for you. Why does a jar of jam, which is obviously super wet, last for years, but a loaf of bread, which feels much drier, gets covered in green fuzz in like a week? It doesn't make sense, right? Well, the answer is going to completely change how you see your kitchen.
Welcome to what I'm calling the food preservation puzzle. And here's the secret clue, the key to solving the whole thing. When we're talking about spoilage, it's not about how much water is in a food. Not at all. It's all about which water is actually free to start making trouble.
I mean, just look at this. It lays the whole paradox bare. On one side, you've got honey and jam. They're practically swimming in moisture, but they are incredibly stable. Then on the other, you have bread and crackers. They feel way drier to the touch, but they go bad in a flash. This is the mystery we're about to crack wide open. So this is the crucial insight, the big aha moment. Not all water is the same. The total amount of H2O a food contains, it just doesn't matter as much as you'd think. What really matters is how much of that water is actually available to act as fuel for those pesky microbes and chemical reactions that ruin our food.
All right, it's time to meet the hero of our story. This is the one concept that explains everything. It's a scientific measurement called water activity, and it's all about that free water factor we've been talking about. So in the world of food science, water activity, or AW for short, is everything. It's a scale that goes from 0 to 1, and it measures only the free water. That's the water that isn't clinging to other molecules like sugar or salt. To give you a reference point, pure water has an AW of 1.0, and something that is bone dry is down at 0. You know, here's a fantastic way to picture this. Think of bound water as a super busy, responsible employee. It's tied up with other molecules, it's got a job to do, it has absolutely no time to cause any problems. But free water? That's like a bored intern with absolutely nothing on their to-do list. It's just floating around, completely available, and ready to help any mold or bacteria that comes along to, start a party. And this chart right here, this shows you exactly why that bored intern, that free water, is so dangerous. Look, most of the nasty bacteria, they need a water activity level above 0.91 to even think about growing. For most molds, that number is 0.80. So if a food engineer can create a product that keeps its water activity below these levels, they can literally stop spoilage dead in its tracks. It doesn't even matter how wet the food feels. Okay, so how in the world do scientists figure this out for every single type of food? Well, they have this amazing diagnostic tool. It's called a moisture sorption isotherm, and it basically acts like a unique fingerprint for every food out there. I just love this quote from the source material. It gives this scientific-sounding graph such a cool, powerful identity. A moisture sorption isotherm, or MSI, is literally the fingerprint of a food system. Every single food has its own, and no two are exactly alike. So, what is it really? Well, it's a special kind of graph. It maps that super tricky relationship between how much water is in a food in total and how much of that water is actually active. Forget a boring chart. Think of it more like a treasure map that shows scientists exactly where all the danger zones are hidden for any food they're working with. And that fingerprint, that MSI curve, it can be broken down into 3 main zones. In Zone I, the water is super tightly bound. It's basically acting like it's part of the solid food itself, totally safe. In Zone 2, it's a little looser, but still mostly contained. But it's Zone 3 you've got to watch out for. That's the danger zone. That's where you find our bored intern, the free water ready and waiting to cause spoilage. Okay, so let's put all the pieces together now for the main event. We're going to build something called the Food Stability Map, and it's going to prove once and for all why water activity is the true master variable when it comes to spoilage. So, here's a fun thought experiment. What if we could take every single bad thing that can happen to food? I'm talking browning, going stale, rancidity, mold, bacteria, the whole shebang, and plot all of it on a single chart against water activity. Well, guess what? Food scientists already did.
And here it is. This is the master chart, the playbook for food engineers. It shows that the specific type of spoilage you get is directly linked to the water activity level. Down at super low AW levels, you still get some issues, like lipid oxidation. That's what makes fatty foods go rancid. As the AW creeps up, other reactions kick in, like browning. And then once you cross those critical thresholds, you get into the real danger zones for mold, yeast, and finally, bacteria. It's all right there.
So let's bring this all out of the lab and back into the real world, back to the supermarket aisle, because now we can see exactly how this science is used to literally engineer the food you and I eat every single day. So how do food engineers control this? What's in their toolbox? Well, they've got a whole bunch of tricks. The most obvious one is just drying food out, right? Like with beef jerky. But they can also add things, solutes like sugar or salt, that bind up the water molecules. That's the secret to jam and cured meats. Even freezing works. It just locks the water away as ice crystals. And a lot of the time, they'll use a combination of these methods to get the perfect, most stable product. Let's think about the perfect potato chip. What do you want? You want that amazing crunch. To get that crunch and to make sure it lasts for months in a bag, it's engineered to have an insanely low water activity, way down around 0.1. At that level, there is practically zero free water, which means no spoilage and maximum crispiness. And now, finally, we can solve our jam puzzle from the beginning. Jam is loaded with water from the fruit, yes, but it is also packed with sugar. And that sugar acts like a powerful molecular sponge, grabbing onto the water molecules and holding them tight. This dramatically lowers the jam's water activity down to around 0.8. That's safely below the level for bacteria to grow, and just on the edge for most molds. It's wet, but it's safe. The water's there, it's just too busy to cause trouble. So really, the big takeaway here is this. The next time you pop open a bag of perfectly crispy chips or scoop some honey that's been in your cabinet for a year, just remember, you're not just eating food. You're actually experiencing a tiny masterpiece of water activity engineering. And that leaves us with one last question to chew on. When we talk about freshness in our modern food supply, this idea of shelf life, are we talking about something natural? Or is what we're really experiencing just brilliant and totally invisible engineering? Thanks for watching.